Okay, so you should be able to see that. Sorry, last week lectures and others went into a different Moodle site. I will fix that one. Okay, sorry for that, but I already fixed that. You should be able to see the PowerPoints. Yeah, and I will fix the videos and everything today or tomorrow morning when I get this week as well. Sorry for that. Somehow it went to another, by mistake I put it in a different last year's course website. Sorry for that. 2021, sorry.
So can you upload the lecture site on the Moodle?
Lecture slides is there.
On the Moodle?
Yeah, you can, is it?
No, I just can week 6.
Week 7.
Week 7, week 8, week 8.
Week 7 not there?
No.
Can you check that one?
Yeah, not here.
Week 7, can you refresh it? Huh?
No. Oh yeah, week 7 is okay.
Yeah, week 7 I put all the video, all the slides there. The only one slide, it will go as a long one. Okay, so you should be able to see the slides, but I will fix the tutorial and other videos very soon. Okay, so I need to do some link may be wrong, so I will fix that one, but the link of the lectures I will hide that one. So but all others can you see or not? Give me a second. I think this. Are you able to see that one, is it? The slides and everything. Okay. So I will continue. So last class the slides are there, isn't it? Slides are there, isn't it?
I just say PC design.
Yeah. So that have full even up to the losses. Okay.
Nature side. Yeah.
Yeah, for the whole things is there.
Okay.
So last week, last class we stopped here. Today we will talk about the tenant profile. Okay, then we will work out a tutorial there. So the tenant profile means so today at 5 o'clock there is a workshop. Okay, I will explain what you need to do. So then we can start, and from next week if you have any question you should be able to ask. Okay. So again I will use the same configuration, simply supported beam. Okay, simply supported beam. So far we work out everything on the center line because this is the critical so this is the critical section. So at the critical section we already found the P value. So he has PI, pre-stress force at this one, PI, and also E value. Yeah, we found those two, yeah, using Macknell diagram. Okay, using Macknell diagram. So now we will see. So because we know we need to provide some steel wires or steel tenons. So how that will go? So whether it's a straight line, okay, whether it's a straight line or in different shapes. Okay, so we don't know the shape of the tenon. We don't know the shape of the tenon. You know the shape of the tenon is here. So at this stage we don't know how that will go. Yeah, it can be straight line or it can be a curve. So to find out that, what we do is we will consider an arbitrary section at distance x. Okay, so we will consider an arbitrary section at distance x. So if you have this one, what we need to find out, the that one, yeah. So where is the tenon will be? So technically we need to find out the eccentricity at distance x. So if you have that one, then you can change the x and you should be able to find out all the values. Yeah. So we need to find out the eccentricity at distance x. Okay. So for this beam, we know the bending moment diagram. It's like this. Yeah. So at distance x, the bending moment mx. Yeah. So what is the equation for this one? Yeah. So because if you have something like this, yeah. So by x equal so this one is the bending moment equation for simply supported. So at distance x, the mx is given by this. So my objective is this one. Yeah, objective is this one. So if you look at this, the inequalities, we have a transfer. So if you look at these inequalities, okay, so this one for the top fiber, yeah, and bottom fiber, and similarly you have 2 for service stage, yeah. So if I write that inequality, so this is a transfer, yeah. So a transfer at this location, distance x, the distance x, what is MD value? So earlier at the midspan, what is MD value we use? In the midspan here we use WL squared by 8, yeah, for the maximum, yeah. But here at distance x, so MD, we should put this one as this one, mx, yeah. So MD as a function of x, okay. So what about the I will not change, same YT will not change, yeah. Area will not change. What about the P, pre-stress value? What about that one? PI is here. I need to apply the PI here, yeah. What about here? So here we found PJ, yeah, jacking force, PJ here. We need to apply some extra force because there is a friction loss, yeah. There will be a friction loss. We discussed yesterday.
Yeah.
So if we want the PI here, this will be slightly larger because of the friction loss, isn't it? So if it is a 5,000, here 5,200 something, yeah? Isn't it? Yesterday we discussed this one, PJ. If it is a 5,000, we might get here around 5,260 or something.
Yeah. PJ.
Okay. Yeah, PJ is here.
1 plus fraction.
Yeah,
loss.
so that's here. Okay, so that means the force should be larger when we go towards the jacking load. So the P here will be larger than that one. Yeah?
Yeah.
So P is equal to Px at this location, Px equal to Pi 1 minus friction loss. Yeah, because the friction loss from here to there.
Okay.
For this one, we found friction, this one equal to Pi divided by 1 minus friction loss. So that is from here to there. friction loss. To find out this one, we need to consider the friction loss here.
The friction loss is given.
Yeah, there's an equation. So I will tell there's an equation in the standard.
Oh,
We can find it.
okay.
Okay. So if the friction loss, there's an equation. We'll talk about that one next week under the losses. Okay, but at this stage you can think that is given. Okay, or you should be able to find out. So what is this friction loss? The friction loss between this point and this point. Okay, whichever the points you are considering, the friction loss between these two. Okay, because Pi 1 minus friction loss, so friction loss from here to there. Okay, so when we find the force here, we consider friction loss from here to there. So we know that one. So we substitute. So the Pi also known. So that is here. Okay, we will substitute this one. So this will be a function of x. Okay, this is a function of x. This is a function of x. This is also a function of x. So we know everything except the E value. E is the one we need to calculate. Yeah. So if we substitute everything, okay, if we substitute everything, you know this one, this one, this one, everything. So the MD and Pi are functions of x. Yeah, it is not a number because it's x. Okay, so if you substitute, what will happen? So you put it each one, and if you rearrange, you will get there is a function. Yeah, there is a function. So I will say this one as a f1x. Okay, so if you substitute and rearrange it, clear? So that is the first condition. Okay, so if you draw the line, this is x. Okay, this is x and this is E, eccentricity. So if you draw the graph, okay, if you draw the, because this is a function of x, yeah. So if you draw the graph, you will get something like this. So this is up to the center line, L/2, up to here. Okay, and you can draw the other side as well. Otherwise, we put it full one. L. So this is L/2. Okay, so this is halfway and this is full. Yeah. So if you draw the graph, you will see this is the f1 function. Okay, so you will see a graph something like this. And you will find E is less than that, below that one. Okay, so similarly, at transfer, this is for top, this is for top, and for bottom.
Same.
Okay, for bottom we have MD upon I YB plus PIA plus PIE upon I YB sigma CS. Yeah. So here you substitute the MD and PI, so you know everything, and if you rearrange it, you will get another function. Yeah. So that is second one. Okay. So you will get another line. You'll get another line, something like this. Okay. So this is for F2. And we have another 2 for service. Yeah. This is for transfer, top and bottom. And similarly, you should be able to get another 2 lines. That is above so finally you will see one clear area. You will see a clear area, something like this, that will satisfy all 4 conditions. Okay, if you draw all 4 lines, you will get a zone that will satisfy all 4 E values. So that will looks like something like this. Okay, so that means within the green color, okay, you will get all 4 inequalities for eccentricity will satisfy. Okay, so that means you can provide the tenant within that zone. Okay, so your tenant should be within the green zone. So if you can provide the straight tendon, that should be okay. Otherwise you need to provide in parabolic shape. So in this case you can't provide straight tendons because straight tendons will not work. Yeah. So if you draw a horizontal line, it will not go through the whole things. Yeah. So in this case we will go with a parabolic shape. Okay. In some cases you can have straight tendons. Okay. In some cases you can have straight tendons, especially when you analyze the slippers, you should be able to see the straight tendons will work. Okay, straight tendons will work. Okay, so the question is should I do like this? It is quite complicated because this is a function of x, yeah, and this one is another function of x, normally the exponential function, e to the power something. Okay, exponential function here. So when you put everything, this one, okay, is easy to tell, but if you work out, it becomes more complicated function. Okay, it have some exponential function e to the power, yeah, e to the power minus mu, something like that, this friction loss equation. Okay, so that is much complex. And also because you have a simply supported one, I write this equation. Okay, but if it is something like this, what to do? You can't write the equation like this, isn't it? For this bending moment, the bending moment diagram will look like this, isn't it? Yeah, the bending moment diagram looks like this. Can you write the equation for this? Very difficult. Okay, so when you put all the things here, this is very complex, this is another complex, yeah, so this one become very, very complex function. So if you want to do that, it will take lots of time. Okay, so what we can do, so rather than doing this one, we will do some simplified way. So what we do is, we take the beam, can be for any beam, okay, it can be simply supported or the continuous, whatever. Okay, yeah, and we draw the bending moment diagram. Okay, so we work out at the critical section. We work out at the critical section. So this is done. Yeah. So that one is Pi and eccentricity we already calculated using Maxwell diagram. So now we need to know the other places. So what we do is, we will rather than consider x distance, we divide this one into equal parts, say maybe, so I will consider 1, 2, 3 separate section, 1, 2, 3, so this one say L by 8 equal, yeah. So you should be able to find out the bending moment diagram if you have the bending moment, sorry, you should be able to find out the bending moments at each locations, yeah. If you draw the bending moment diagram, you should be able to find out the values, isn't it, at this point, yeah, you should be able to find out the values. So in this equation, say for the top, minus md, in this equation, or any four inequalities you have already, what you can do, you can find out that value. So at L by 8, you calculate, you find out the moment and substitute here, okay, and at this one you can find out the friction loss, yeah, and put it here. So you calculate everything, okay. At this location, in these inequalities. So if you substitute, this one is a number, yeah, everything is a number other than E. So you will get E less than or equal to something millimeter, a number, okay. It can be, say, less than 50, yeah, or 150, whatever, yeah, it will give a number. So you will have 4 inequalities, 2 for transfer, 2 for service. In each one at L by 8, at L by 8 you will find out. So you have 4 values, E less than or equal to something, E greater than something, then E less than something. So you'll have 4 values, okay, because 4 inequalities you have. So then you can say that less than 150, and so you should be able to find out a range, yeah, and you can say, okay, this is within this range, so you can select the E value for L by 8. So then redo the same things here, then you should be able to find out and draw the profile, okay. Any questions? So here what we do is, rather than doing the work for arbitrary section, rather than doing the work for an arbitrary section, we will do at particular locations, okay. We will do it for particular locations at L by 8, L by 4, 3L by 8. So you have some points, then you can have a nice profile, yeah. So this is how normally we do the tenant profile. Either develop a feasible zone as I explained earlier, you can develop a feasible zone, or you can do at various sections and find out, okay. So this is the second question we want to discuss. Okay. So this one is about a cantilever beam. A cantilever beam. You have a moving load, 5 as 250 kilonewton, and you need to find out pre-stressing force and where the tenon need to be placed, okay, and then we have to put the tenons. So this one tutorial question, it's a cantilever beam with 250 kilonewton, yeah. The bending moment diagram, like that, yeah. This is PL. For cantilever with the uniformly distributed load, the bending moment diagram, This is the bending moment diagram. This is WL squared by 2. Okay. So L is 5 meter. 5 meter a cantilever beam. Okay. $5 cantilever beam. Okay. So how this beam will bend? The deflected shape under the normal loadings, beam, you have some self weight, and point load. It will deflect like this. Yeah, this is the normal deflected shape, isn't it? The cantilever beam will bend like this. Yeah. So where is the tension? So tension will be on the top. So we will have a tension on the top, compression on the bottom. Okay, tension on the top, compression on the bottom. Is that okay? So we need to, let's say this is the neutral axis. That is a neutral axis. So the top part will be under this one, tension. So we need to apply the compressive force on the tension zone. So we need to apply a compressive force on the tension side. Yeah, so we need to apply the compressive force on the tension side. So it will be on the top. Yeah, so your cable will be in that zone. Yeah, the cable will be the top zone. Okay, because whole beam will be bends like that, so it will be under tension on the top. Okay, so we need to provide the steel part on the top, So the question is, we need to analyze and find out the pre-stressing force first. Yeah. So if we apply the compression on the top, this is the deflected shape under service. Yeah. This is the deflected shape under normal service load. So at transfer, how that will look like? Because this is the curvature, this is the curvature under the normal service load. Yeah, under the normal loading. So at transfer, so what we'll have? No load other than self-weight. So we don't have this force, yeah, only self-weight. So still bends like this, but if we apply the pre-stress, what will happen? It will bend in opposite direction. So it will bend in the opposite direction because we apply the pre-stress on the top zone. So the deflected shape at transfer will be opposite to the service. Okay, remember that one. So the top part will be under compression, bottom part will be under tension. Okay. Clear? You need to understand, earlier I use simply supported. Yeah, I use simply supported beam. So under the normal service load, it will bend like this. Yeah, the beam normally bends like this. Yeah, when you apply the load, it will bend like this, isn't it? That's normal. So at transfer, that is a new case we studied. It will be opposite direction. So the curvature will be opposite to this one. Okay. Since bottom part is under tension, top part will be under compression normally. So we apply the compressive force in the bottom zone. Yeah. So here we apply the compressive force at the bottom zone. Because bottom part will be under tension when you put the full load. Yeah. But here the top part is under tension. Okay. So we put wherever the tension, we apply the compressive force. Okay. The pre-stressing force should be applied at the tension zone. That's what we discussed in the first class. Okay. So if you have something like this will bend in opposite direction. So this one and this one will be opposite to each other. So you can see, okay. So it is not always transfer will go like this, okay. It is not the case. So it depends on how the beam will bend under normal loading. If the beam bends downward, if the beam bends downward, a transfer it will be opposite to that one, so that means upward deflection. So under the service normal load, if the beam bend downward, a transfer it will be upward. Okay, so the curvature will be opposite, so tension on the top, compression on the top. Okay, clear? So now, which is the critical section? So in this one, we look at the middle section, yeah, isn't it? Because the bending moment diagram is like this, maximum is here. So the critical section is in the mid span. The critical section is in the mid span because that have the largest bending moment. Yeah. So in this case, which is the critical section? Where is the critical section is? Where is the critical section? So where is the maximum bending? If you look at the bending moment diagram, maximum bending will be at the support. Yeah, the maximum bending will be at the support. So since maximum bending is at the support, the critical section is this one, at support. Okay. So I need to consider the cross section, this one, because I need to analyze the critical section first. So I need to find out the pre-stress force and the location at the critical section here. So that means somewhere here I need to apply the pre-stress force. So I need to find out the eccentricity. Yeah, so definitely in the top because it's under tension, top part, not in the bottom. Okay, the pre-stress will be on the top. So if you look at the cross section, I just draw as a rectangle. We'll come to that right in a minute. Okay. So if you have something like that, this is the neutral axis. So your pre-stress will be somewhere here. So I need to find out E value. Okay, I need to find out the E value. Remember, this is the other side. Okay, so your bending moment due to this is the moment due to dead load, yeah, and Pi is here, and that is eccentricity. So this eccentricity will give a moment. So that is PIE, that is due to the eccentricity. So if you draw a transfer, so if you draw the stress blocks, due to moment, top part will be under tension, bottom part will be under compression. So opposite stress block, careful, due to loading, due to self-weight, and then due to pre-stress, then due to eccentricity, that will turn like that. So here you'll have compression, here you'll have tension. So the curvature, so top part will be under compression, bottom part will be under tension. Okay. So you need to write that stress equations, and you should be able to find out. You should be able to find out two inequalities. Yeah, you should be able to write the stress, and you should be able to find out the inequalities. That is normally, I will upload this one as well. You should be able to write that for the top compression, and you write that one, and bottom tension, write that condition. So similarly at service, the same case, use the YT and others, okay? Don't use the H/2, YT and YB, because then you can use for any sections. So this is PE, effective pre-stress. You have a moment now, moment increase because full load, MS, is MS. So the stress blocks are almost same, doesn't change the stress blocks, but the values will change. So here it will deflect. Top part will be under tension, bottom part will be under compression. So top under tension, bottom under compression. You need to write the inequalities for these two cases. Okay, so you should remember, you should be able to write. So you should be able to work out, and if you once you write that 4 inequalities, please work out, okay? So if you work and then you look at these two, combine these two, the bottom ones together, top one together, so you will get this one. Okay, set B. You should be able to get this one if you write the two inequalities correctly. Okay. So if you substitute, I put this document on the website, so you will get something like this. This is for the tutorial 2, the second question, okay? So you have this, and if you put this all the values, your bending moments, yeah, MS and MD, I wrote there. You will find this one is large, 69, which is here. Okay, this one is larger, the bottom one is smaller. So in the previous question, the tutorial 1, we have simply supported beam. We had simply supported beam. Over there, ZB should be larger. Okay, if you remember. ZB is larger. Okay, because the bottom part is under tension. So we need large section modulus wherever you have tension. Okay, but in the second question, the top part is under tension. The top part is under tension. So the top section modulus require large value, or the top section require large section modulus. Okay, so the large section modulus is on the top, so it need to be 69. Okay, so what you need to do is, this is the requirement. Okay, so when you use the I sections, use the smaller section, find out what is the requirement. Then if it is not satisfied, go to the next one. Okay, so it says type 3 will work. Okay, so then I give the solution for these inequalities. If you substitute, you will get that these are the inequalities you will get for 4 cases. Okay, and these are the numbers you will get. So I will upload this one. I will upload this document. Okay, but please write this one. This is important. You should understand how to write it. Okay, and the final answers are given. So please work out there. Okay.
For every question, we need to calculate the two kind of state, like at the transfer and at the service.
Transfer and service. Yeah. Okay. So that is about the tutorial. Then you can work out where to put this one. And I need all these inequalities to work out. So please work out. Then the whole tendons will be on the top. Okay, I will upload this the solutions, and when we go each and everything, so I will add one by one. Okay. Okay. So now let's move on to the next topic. Now we will see how to work out ultimate moment and shear. How to work out the ultimate moment and the shear. So we discussed so far how to find out the pre-stress force and its location, and then we also discussed how to find out number of tendons, and then we discussed how to place them along the beam. Okay, so you need to do this one in your assignment. Okay, so this afternoon I will explain what you need to do, and then from next week, if you have any questions, please bring. So that means you need to start working now. Okay, so this is individual.
तो ऑनलाइन भी दे दें कोचिंग है आइल्स वही बोल रहे हैं अब फरहान भाई से बात हुई उन्होंने ऐसा बोले इतने ट्वेंस हुए थे उनको तब बोले फिर देखेंगे अभी तो कुछ भी नहीं हुआ अब वो 6 months 8 months.
Hello, please mute it. Okay, thanks. So now we will see, because the cracking control criteria has been used, so we will look at the ultimate strength. If you want, you also can calculate the deflection, but the deflection will be less because we said no cracking. Yeah, if the crackings not occur in concrete, generally the curvature will be much smaller. Okay, the deflection will be smaller, but if you want, you should be able to calculate the deflection and check it. So now the strength limit, so that means ultimate limit state. Cracking, deflection, okay. So then what about the moment? Okay. When you design for a bending moment, or when you design a beam that technically carry the load by developing internal moments and shear. So we need to ensure the moment capacity of the beam is satisfied. Okay, moment capacity of the beam is satisfied. So how to work out that one? So now the load combination is different, because the load combination is for ultimate limit state, so that is 1.2 G plus 1.5 Q. Okay, so far we use G plus long term factor times Q. Yeah, so the load combination we used, the load combination ultimate check, so 1.2 G plus 1.5 Q, because for ultimate, okay, for serviceability, for cracks we use G plus, yeah, this one. So now that finished, now ultimate is 1.2 G, so the bending moment will be much higher. Okay, so we will only consider at service, okay, not transfer. We don't worry about the transfer for ultimate check. Okay, so the moment you will use to calculate the bending moment, this one. Okay, so if you have a section, it can be any shape, but I will use the I section. So this is the ultimate case, this is B, this is D. So the neutral axis will be somewhere here. It is not passed through the centroid. Okay, the neutral axis will not pass through the centroid. It is ultimate case. So this is the neutral axis. So the stress distribution will be like this: compression on the top. So we have the original neutral axis, centroid is here, and we have E value. Yeah. So this was measured from the centroid or centroidal. So this is the previous neutral axis. The previous neutral axis will pass through the centroid. Okay. So the eccentricity was measured. The eccentricity was measured from the elastic neutral axis. But now the neutral axis has changed, because ultimate limit state is not elastic. Okay. So it crossed the elastic limit. So it is here. So this one is dn. Okay, you remember that in concrete, dn. So this is 0.003. Okay. So the stress block, this is gamma dn. So there will be a compressive force. So here we have a steel pre-stress. So that is here. We just put as a PT. Okay. Sometimes not always, but sometimes they also provide some reinforcements. Okay, some reinforcement in the pre-stress bars, pre-stress beams. This is not to carry the bending moment mainly. It will for minimum area and other reasons, and also sometimes this will give some additional moments. So that is FSY, AST. AST is this one. This is APT, area of pre-stress. Okay, sorry, not APT, AP should be okay. Area of pre-stress, AP. This is area of steel. Okay, sometimes they use APT, sometimes they use AP. Okay, so just forget about this one. Okay, don't worry about the FST, AST at the moment. Just leave that one at the moment. Okay, so here now what is FC? That is alpha 2 F dash C gamma dn times B. Yeah, is that okay? So what about PT? What is the pre-stress force? We calculated some pre-stress PI. Yeah, we calculated some pre-stress force earlier, but that one is under the service loads. Okay, we calculated the pre-stress force under the service load, isn't it? We use this load combination to draw the metal diagram. So we calculated the pre-stress force under the service load. Now it is ultimate. Ultimate means the load is much larger. Okay, the load is much larger. So if we increase the load, what will happen? Okay, just consider a beam, simply suppose a beam. Okay, so you have a beam, something like that. You apply the load, it bends, yeah, and if you apply further, it will bend further. Okay, the bending will increase, yeah. So when you have something like this, this is under service, yeah, this is under service, and if you increase further, yeah, so curvature will increase, yeah. So what will happen if you bend further? What will happen for the steel inside? You have the steel inside, isn't it? You put the steel here, yeah, isn't it?
Yeah.
Press the steel. So what will happen if you increase the bending?
The more steel.
Okay, just think about the beam, something like this, yeah. Let's say it's a 2 meter, yeah. So everything is 2 meter, here 2 meter, here 2 meter, everything is 2 meter, yeah. And it's now bends. What you can tell about the length of the bottom fiber here? This will be more than 2 meter. It will be stretched. This is under compression, so this is less than 2 meter. Yeah?
Yeah.
So overall won't change, but the bottom fiber will be stretched. The tension side will increase the length. Yeah? The top part will reduce its length. That's under compression. That's what we call compression. Okay? So if we increase the load further and further, it will bend further and further. So the length will increase further and further. Yeah? It's not a couple of meters, it's millimeters, okay? The increase will be in millimeter. So when you increase the load, from here to there, service load to the ultimate load, the bending will increase. If bending increases, it will have more curvature, yeah?
Yeah.
So that means the steel, because that steel is in the tension side, yeah? So tension side will increase its length, yeah? Tension side, the length will increase. Since the steel is in the tension side, so that length will increase, okay?
Steel.
So the steel will stretch further. So you stretching the steel even further. So when you stretch the steel, what will happen? That will have more compressive force. Yeah? Because when you stretch the one, it's under tension, it tries to give more and more compressive force. So the pre-stress force at ultimate, will be larger than what we calculated earlier. Yeah? So you can't use the same pre-stress force here. So we can calculate, because we should be able to find out the strain. Yeah? This one is known. You should be able to find out the strain using similar triangle, isn't it? Yeah? So you should be able to find out the strain, then you should be able to calculate the stress. Yeah? You should be able to calculate the stress. Okay? So this strain is addition to what we applied earlier. Okay? So then you should be able to calculate what is the current pre-stress force. You should be able to calculate what is the current pre-stress force. Otherwise, you should also use this equation if you don't want to calculate the strain and do the work. This is the standard, this is the maximum it can go. Okay, so if you look at this, the stress strain relationship, so this is the yielding one, yeah, you remember that this is the breaking one, this is the yielding one, yeah. So under the service load, we don't want to exceed our pre-stress, we don't want to exceed the pre-stress, so we put somewhere here. Okay, we were sitting somewhere here within this range, yeah. So we don't want to exceed that one, so we don't want to exceed that the yielding point, so we might, our loadings will be somewhere here, yeah. But when you have ultimate, normally that will be around somewhere here. This is serviceability range, this is ultimate range. Okay, clear? So the K1, K2, you go to the close number 817 in the standard. Okay, AS3600, AS3600, you should be able to find out. Okay.
And how to calculate the FPV?
That is given in the
It is given.
3.3, close 3.3. Okay, so FPB, go to close 3.3. Okay, there's a table.
Okay.
So if you had two forces, if no reinforcement, if you don't have any reinforcement, this is equal to that, isn't it? This one should be equal to that. If you don't have this one, yeah, FC equal to PT, yeah. So alpha 2 F dash C gamma dn B FPB 1 minus K1 K2 upon gamma AP. So you should be able to find out dn, yeah, you should be able to find out dn, then check for dn. What is a check? Dn upon d, yeah, okay. So once you have this one, what is the distance? What is the distance? The moment? mu pt times z1, because we have equal force. Yeah. What is z1?
0.
From top to bottom, from top to bottom. So this one is a yt. Yeah, that is yt, and this is yb, isn't it? Earlier, the neutral axis earlier, yb and yt. So from top to here, from here to there, yt plus e. Yeah, yt plus e from here to there. Then this one, half of that, minus half dn by 2. Okay, so you should be able to calculate and check m star less than pi mu, and if it is okay, that's okay. If it is not satisfied, what we need to do, we need to add reinforcement. Okay, so we might need some reinforcements. So if you have reinforcement, what is the condition? Fc equal to Pt plus Fsy Ast. Okay, so assume Ast and calculate dn. So here you need to assume this one, okay, otherwise it's difficult. Assume this one, okay, assume this one and calculate the dn. So this is alpha 2 f dash c gamma dnb equal to fpb 1 minus k1 k2 on gamma ap plus fsy ast. Okay, so you assume and you get the dn. Check for dn. So now how to find out the moment? Easy way is to take the moment from here or there. Okay, so I take the moment from here. So this one both. Okay, so this one will rotate this way, this one will rotate that way. Okay, so moment mu fc d minus gamma dn by 2 minus pt times the distance yt plus e, d minus yt plus e. So then you have the mu value. Okay, so you should be able to find the ultimate moment and check whether minimum reinforcement still need to be provided, yeah, if it is a bending member. Okay. That is quite straightforward. But in the I section, little bit complicated. If you have, because this is a rectangular section, but if you have I section, so if you have gamma dn, and you need to consider this area, okay, so not the gamma dnb, so you need to calculate this area. So this is the area of this one, isn't it? Gamma dn is here, so this is gamma dnb, yeah. So if it is a rectangle, it's easier, but if it is other shapes, you need to find out that area, that's all. Otherwise it is not difficult.
Yeah.
Okay, so normally in pre-stress we use some I sections, so you need to calculate that one. Okay, sometimes that gamma dn will be in the top part. Okay. Okay, so the next one is the shear. The shear also same as what we learned in the RC design. VU is equal to VUC plus VUS. Yeah, we have an additional term here, PV. Okay, in reinforced concrete design, we studied same clause. Okay, same clause. If you go there, the ultimate shear capacity, nominal shear capacity VU is equal to VUC plus VUS. Yeah, but we have an additional term PV. We have an additional term PV. PV is the pre-stress component. Okay, so wherever you calculate the capacity, there will be a pre-stress, yeah, the vertical component of the pre-stress. So what is vertical component? So if you have pre-stress, if you are calculating the shear strength here, the vertical component, pre-stress is going like that, yeah, pre-stress force is going this way, yeah. So the vertical component, you apply the pre-stress this way, the vertical component, this is PV. Okay, so if you know the slope, then your P sine alpha. It's not difficult if you know the slope of this one. So if you calculate the shear stress here, it is horizontal, vertical component is 0, PV is 0. Okay, so PV is 0 here because pre-stress is in the horizontal direction. If you have something like that, okay, so the PV is the vertical component, so it's not difficult one. Okay, so VUC is equal to KV times BV, you know how to calculate that one, yeah, and the theta V also. So only different here in the pre-stress things, we have an additional term PV, we have an additional term PV, and also when you calculate the KV and theta, we cannot use the approximate method. Okay, what does that mean? So if you look at this ES3600, this is the shear stress things. So for kV and theta, so this is the kV and theta calculation method, okay, but in the RC design we use approximate method. What is the close number? To find out kV, I think 8.4 or something.
8.2.4.3.
8.2.4, isn't it? Yeah. This is general method. Okay, so this one. So we use this method, simplified method in the RC design. Yeah, you remember? The kV is equal to this one. In the RC design, we use this one. But this is only valid for non-pre-stress members. Okay? If you don't have pre-stress only, this is valid. So in RC design, this is okay. But in PC, we cannot use this equation for kV and theta. Theta is 36. In RC design, we use this one, yeah. And kV is this one. But in this one, we need to use the general method, not simplified method. So it should be this one. So theta V is this one. The kV is given by this equation, this or that. Okay. So you need to use this clause to find out theta V and kV. We will work out in the tutorial. Okay. So the kV and theta V, we should use a general method because the simplified method is only valid for non-pre-stress components. Okay, non-pre-stress component only we can use the simplified method. So in RC design, that's okay. In RC design, that's okay because we don't have any pre-stress component. But here we have pre-stress, so we had to use the theta and k using this one. So only different is we need to find out the epsilon x, the strain in the x, longitudinal strain. So we give the equation here. Okay. So this is only a little bit extra work in the pre-stress. Okay. Otherwise, it's if you have this the strain, you should be able to put it here or wherever the correct one. So you should be able to find out the theta v. Okay. So in the RC design, simplified method is valid, but in PC is not valid. Okay. So we will work out the tutorial. So that is the next the question. We will work out this one in the next class. So next Monday we will work out the tutorial 3. Then we will look at the losses. Then that's almost end of the. So next Monday we should be able to finish most of these pre-stress. Week 10. Okay. So then week 11 we will have drop-in session if you have any problem with this one. Week 12 we will do. We don't have any class in week 11, but I will be here if you have any problem with the project. Okay. Try to submit it on time, because then exam. Okay. You can't. So that's what we try to finish it early. Week 10. Week 12 will be revision. Okay, so I will go through all the RC and PC design in one class, what you need for the exam. So try to clear up this assignment quickly, then you can prepare for the exam. If you have that one, you can prepare for the exam. Okay, so open book. Open book doesn't mean you will have same question from the tutorial. Okay. So
just to change the number.
we'll see. Okay. So it's not a difficult exam. It's not a difficult exam, but so that is. So then we will. It is not a difficult exam, but we need to prepare. So week 12 will be the revision one. So the next week will be the last week for the lectures and tutorial. But week 11 I will be here. It's not cancelled. Okay, I will be here. So if you have any questions, if you have any problem in the project, you can ask. Okay. If you don't have any question, no class. So, but please start working now, otherwise it will be difficult. So the connection will disconnect in 2 minutes. If you have any questions or anything. Pre-stress also individual or team? I will double check that one.
Teams.
Team?
Yeah.
Yeah, okay, I will double check that one, because I have a couple of things. But if it is a team, make sure you have the teammate also work and start to work there. Okay, I'll confirm that on this afternoon, 5 o'clock. Yes, I have 4 units. Sometimes I might confuse which one is teamwork, which one is individual. So, okay. Okay, so I think it's any other question. We have only 1 minute, or sorry, 2 minutes there. Sorry for that. The videos may not appear after week 6, so I will update everything tonight or tomorrow morning. Okay. But you have the PowerPoint, and I will also upload the tutorial. Sorry, I put it in a different unit. It's a very okay. Okay. Any other things? Okay, otherwise we will see you at 5.